Okay, you guys, good morning. Let's talk a little bit about fission and fusion. So these are, like it says, two general types of nuclear reactions. Again, this is happening inside of the nucleus, hence nuclear. Fission is the process of splitting a very unstable, heavy nuclei into some smaller nuclei, and in turn, energy being released. Nuclear fusion is taking smaller, lighter atomic nuclei and putting them together to make a heavier nuclei and lots of energy. So nuclear fusion releases a lot more energy than nuclear fission. Nuclear fission is the type of nuclear reaction that occurs in a nuclear power plant. Nuclear fusion occurs in the sun. Nuclear fusion produces way too much energy in order to actually have that reaction done in a nuclear power plant. Way too much energy to harness, and byproducts are very dangerous too. Okay, so let's talk a little bit about some of these terms here. Binding energy, the energy that holds the protons and neutrons together. That seems pretty normal. There has to be some sort of energy that's present when those protons and neutrons are held together in the nucleus. So when there is a change in the nucleus, what happens is this binding energy is the energy that is released. Okay, so there is an energy that is between the protons and the neutrons in the nucleus. It's called the binding energy. When that is changed, when the nucleus is changed, it is the binding energy that is released. And that binding energy could be in the form of gamma rays or heat rays, whatever is being released. Now, the binding energy is also called the mass defect. So, kind of weird. And I don't have my little drawing tool here. Not weird, but if you guys know, I'm sure you know Einstein or know of him. Einstein is famous for his equation, and E is equal to mc squared. So basically, this is the deal. Let's say, for instance, you find the mass of the nucleus of an oxygen atom. Okay, so if you find the mass of the nucleus, let me start over. If you find the mass of the nucleus of an oxygen atom, you are going to get 15.99 AMUs. However, if you were to take the mass of each individual proton and neutron in the nucleus of an oxygen atom, and if you added all of them together, you're going to get 16.13 AMUs. So there is a little bit of a difference there. So what happens is that difference, that mass between all of the individual particles, okay, added together, and the mass of the entire nucleus, that difference in mass, that mass actually changes into energy, and that is our binding energy. It's a little kind of complicated to wrap your brain around, but that's where that E is equal to mc squared. So this difference in mass, okay, that mass turns into energy, and that energy is the binding energy, and that's what is released from the nucleus of an atom in fission and fusion reactions. So let's look at nuclear fission a little bit better. It occurs in really large nuclei. Uranium-235 is probably the most popular fissionable isotope. So, as it says, when the electrostatic force pushes, the force that pushes protons away from each other is stronger than the nuclear force that holds the protons and neutrons in the nucleus, the atom becomes unstable. So it's like a tug of war, the electrostatic force versus the strong nuclear force. One is pushing the protons away from each other, and the other is trying to hold the protons and neutrons together. So when there is a unbalance between these forces, the nucleus becomes unstable. So most common isotope to undergo fission reactions is uranium-235, polonium-239 as well. So this is basically what happens. You have this uranium-235 isotope. It is bombarded with neutrons, this N1 over 0. It is bombarded with a neutron. That neutron breaks that isotope down. It breaks it into 2 new isotopes and 3 more neutrons. What happens is those 3 neutrons seek out 3 more uranium. Hi. Okay, sorry about that. My neighbor's dog came running in. Okay, so uranium-235 is bombarded with neutrons. A neutron hits this isotope, breaks it into 2 new, more stable isotopes. In this case, barium-140, krypton-93, and 3 more neutrons are released, and so is a whole bunch of energy. This energy could be heat or gamma rays. So if you remember on the electromagnetic spectrum, the highest energy electromagnetic radiation are gamma rays. Another product besides barium-140 and krypton-93, this reaction could also produce strontium-90 and xenon-143. So as you can see, in the product, you have 3 neutrons that are released, and what happens is those 3 neutrons will seek out 3 more uranium-235 isotopes and hit into those. And then each of those will produce 3 more neutrons, and then those 3 neutrons will seek out 3 more uranium-235s, and so on and so forth. And that's called a chain reaction. Kind of like dominoes, a continuous series of nuclear fission reactions. So each fission reaction is going to produce 3 neutrons. Those 3 neutrons will seek out 3 more uranium atoms, each of which will produce 3 more neutrons, and those neutrons will again seek out 3 more uranium atoms, and it just goes on and on and on until there's no more uranium atoms to split. That is a chain reaction. I don't know why I have this, oh no, there are several different ones. Let's see. Yeah, make sure you watch, I think this one, they might be the same, but check out each of these. HIU, chain reactions. Oh yeah, they're each 3 different videos. Make sure you guys watch those, okay? Okay, so nuclear fusion. Fusion, just like it says, it's fusing lighter nuclei together to make larger nuclei and producing a whole boatload of energy. This happens in the core of the sun, happens in the stars in the sky, and it's these fusion reactions that power the sun, that produce all of that heat and light energy for us. This is basically what happens. You have 2 hydrogen 1 atoms, they fuse together and they produce a hydrogen 2 isotope. A positron is produced, and so is a bunch of heat energy. This hydrogen isotope, okay, which is right here now, this hydrogen isotope now fuses with another hydrogen isotope to produce a helium isotope, and a bunch of gamma rays are released. That's high energy. It's a lot of energy. This helium-3 down here is now a reactant, and it fuses with another helium-3, and it produces a helium-4 and 2 hydrogen atoms and a bunch of gamma rays. And then it just, these 2 guys, okay, it just starts all over again. The 2 hydrogen isotopes produced start the process all over again. So it's basically kind of like 3 reactions to get all of this energy for fusion reactions. Okay, so like I said, please make sure you guys are watching these 3 videos. It gives you a good explanation of fission versus fusion. I hope you guys are well. I miss you. I realize it's getting close to Christmas vacation. It's not right now when I'm recording this, but when you're watching this, I think it's getting close. So take care and be good. Bye.